Today's video is all to do with physics, AQA GCSE, and we're going to be looking at the required practicals for paper 1. So I'll be taking you through all the theory followed by past paper questions. So you should have a really full understanding of what's going on by the end of this video. Let's start with our definition of specific heat capacity. It is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. In terms of an equation which uses specific heat capacity, you're probably familiar with E equals mc delta T. So E is the energy change. M is the mass of the substance, C is your specific heat capacity, and delta T is your change in temperature. So you could be asked to find any of these quantities in the exam. Now it's possible to experimentally determine these values, so I'm going to start by showing you how you can find the specific heat capacity of a solid followed by liquid. So always bear in mind your equation, E equals mc delta T. Because we're after specific heat capacity, we'll want to find C. So just make sure you rearrange that equation appropriately. So it's energy change over mass times by the temperature change. So we need to use an experiment in order to find E, M and delta T, which will enable us to find C. So I'll go through those steps now. First of all, find the mass of the solid. Always mention apparatus. So we find the mass of the solid using a balance. We need a way of heating our solid, so actually we're going to use an immersion heater to do that. Because we need to be able to measure temperature change, we're going to place a thermometer into a second hole in the solid. We don't want to lose a lot of energy to the surroundings, so it's quite important to insulate our solid simply using something like cotton wool. So we know that we can find the mass, M, using the balance. To find delta T, so change in temperature, we want to measure the temperature before, turn on the heater for 10 minutes, and then measure the final temperature. And so because you found the final temperature and the initial temperature, that will enable you to find delta T. So if we constantly refer to our equation, we know we can find the mass, we know we found delta T. How do we find the energy transferred? Well, you'll need to use another equation, which is E equals PT. So that means we're going to use the power of the immersion heater as well as the time it's switched on for, which in this case was 10 minutes. Which let's convert that into seconds because that's the standard unit, which is 600 seconds. So now we have enough information to feed into specific heat capacity equals energy change over mass times temperature change, and that will enable you to find the specific heat capacity. So with physics, it's always important to be using the appropriate equations and then mention the various apparatus that will enable you to find these different parts of that equation. You could be asked to find the specific heat capacity of a liquid. So rather than obviously inserting an immersion heater and a thermometer into a solid, this time you're going to place that liquid into a beaker. Then you're going to add a heating coil and a thermometer, but it's going to be very, very similar. Figure 2 shows the equipment a student used to determine the specific heat capacity of iron. The iron block the student used has 2 holes, one for the heater and one for the thermometer. Before the power supply was switched on, the thermometer was used to measure the temperature of the iron block. The student left the thermometer in the iron block for a few minutes before recording. The initial temperature suggests why. It's only worth 1 mark, and that's to make sure that the thermometer temperature was the same as the temperature of the iron block. Figure 3 shows how the temperature changed after the power supply was switched on. The energy transferred to the iron block between 5 and 10 minutes was 26,000 joules. The mass of the iron block was 2 kg. Calculate the specific heat capacity of iron. So here's the equation we want to use. Specific heat capacity is energy divided by mass times change in temperature. So we know that the energy transferred was 26,000. The mass we were told was 2 kilograms. The temperature change needs to be between 5 and 10 minutes. So you need to use your graph here. There's 5 to 10 minutes. Read across nice and carefully. So that's 54 degrees Celsius, 28 degrees Celsius, giving us a temperature change. So the difference between those two numbers is 26. Pop that into your calculator and you'll get a specific heat capacity of 500. The student repeated the investigation but wrapped insulation around the iron block. That's going to stop heat transfer to the surroundings. What effect will adding insulation have had on the investigation? You need to tick 2 boxes. The calculated specific heat capacity will be more accurate for sure. The iron block will transfer thermal energy to the surroundings at a lower rate. Yeah, I'm happy with that one. Let's just check the other ones. The power output of the heater will be lower than expected. No, it will have no effect on that. The temperature of the iron block will increase more slowly than expected. Absolutely not. The uncertainty in the temperature measurement will be greater. It's got nothing to do with how you read the thermometer, so I'm confident that options 1 and 2 are correct. A student investigated the thermal conductivity of different metals. This is the method used. Measure the mass of an ice cube. Put the ice cube on a metal block which is at room temperature. Measure the mass of the ice cube after 1 minute. Repeat with other blocks of the same mass made from different metals. Table 3 shows the students' results. The initial temperature of each ice cube was minus 15 degrees Celsius. Why was it important that the initial temperature of each ice cube was the same? Obviously, we need the starting temperatures to be the same because after all, we're going to have an independent variable, which is the type of metal that the ice cube is placed on. So clearly, the initial temperature is a control variable. Which metal had the highest thermal conductivity? Give a reason for your answer. So you're looking for the greatest change in mass. It's here, 5.93, and it belongs to copper. Suggest one source of random error in the student's investigation. So random error is an unpredictable variation in measurement which causes a slight change to the result away from the true value. So think about this critically. You could have variation in the initial mass of the ice cube. It could be that the ice started melting whilst you were handling it. The room temperature could show variation. An ice cube has a temperature of minus 15 degrees Celsius. The total thermal energy needed to raise the temperature of this ice cube to 0 degrees and to completely melt it is this much energy. Here's your specific heat capacity of ice. Here's your specific latent heat of fusion. Calculate the mass of the ice cube. This is a difficult calculation. You're going to need to use 2 equations. One is E equals ml, which states that energy is mass times latent heat of fusion. The other one is E equals mc delta T, which states that energy is mass times specific heat capacity times the temperature change. We know that the temperature change is 15 because we know that the ice cube's going from minus 15 degrees to 0 degrees Celsius. We're after the mass, but be very careful here. You need to read this line super carefully. It says that the total thermal energy needed to raise the temperature of this ice cube to 0 degrees Celsius. So that is your E equals mc delta T, and to completely melt the ice cube. So that's all to do with a change in state, which is your E equals ml. And because those values are different, that's why I've labelled them E1 and E2. And we can therefore see that those two energies added together equal 5848 joules. You're going to have to be so careful there. So I'm just going to rewrite that here. Then I'm going to sub in what E1 equaled, which was mc delta T. And then E2 equaled ml. We can take m out as a common factor, so your maths needs to be on point here for this question. After all, we're after mass, and then it's just a matter of subbing in all our values. We know that C is the specific heat capacity. I've already worked out that the temperature change is 15 degrees. The latent heat of fusion, we were told, is 334,000. So sort out everything inside that bracket. And then divide both sides by 365,500 to get a final answer of 0.016 kilograms. That is a really nasty question. In this required practical, we're asked to describe how to investigate how the resistance of a wire changes with the voltage across the wire. So we have a voltage value, a resistance value. We're being asked about resistance, so we need to use this equation, which is resistance equals voltage divided by current. So we can clearly see that if we determine both the voltage and the current of our wire, we'll be able to work out the resistance of that wire. So what do we need to add to our circuit? Well, we need a voltmeter to measure the voltage or potential difference, and do remember that that needs to be added in parallel to the circuit, so as a separate branch. And then we need an ammeter, measures current, and that's going to be added in series, so part of the main circuit. Let's draw the circuit itself. So here is my wire. I need a power supply, so I've added a cell to include a variable resistor. As I've already said, I need an ammeter to record the current, which I've added in series, and then I need a voltmeter to measure the voltage, which needs to be added in parallel around the component that we're interested in, and we're interested in the wire, which is why I'm adding it here. So that's what you need to draw if they ask you to draw a circuit of what's going on. I'm just going to write out this method in full now. So we're going to connect an ammeter in series with the wire, take a reading from that ammeter, and that will tell us our current. Then we need to connect a voltmeter in parallel with the wire. We need to take a reading, and that will tell us the potential difference or voltage. Then we're going to use the equation resistance equals voltage divided by current to find resistance. As I've said, we need to include a variable resistor. And then just general experimental points. We need to repeat and calculate an average. Ideally, we'd plot a graph of voltage against current, because if we find the gradient, which remember is change in y, so in this case our change in our voltage reading over our change in x, change in current reading, and by doing that we'll have a more accurate idea of the resistance. And then don't forget your control variables, so that's what we keep the same. We need to keep the length of the wire the same, because after all, the longer the wire, the greater the resistance, the type of metal that the wire is made out of, the cross-sectional surface area of the wire, because the greater the cross-sectional area, the lower the resistance. We also want to keep the temperature the same. And so I'm hoping you can see when I scroll out, I've written a really nice full method here as to how we're going to investigate how the resistance of a wire changes with the voltage across the wire. Now, this required practical is all about constructing appropriate circuit diagrams in order to investigate the current voltage characteristics of various components, including our filament lamp, a diode, and a resistor at constant temperature. So I'm going to show you past paper questions because I think that's the most straightforward way of teaching you this. Let's just have a look though at the kind of graphs we could expect to produce having carried out an investigation into how current and potential difference are related in these various components. So with a wire or a fixed resistor, so remember a fixed resistor looks like this, you're going to find that you get a straight line with a constant gradient, meaning that we've got a directly proportional relationship between current and potential difference. The resistance does not change because, after all, the gradient is unchanged and the gradient will tell us the resistance, and as a result we can say that this obeys Ohm's law. And Ohm's law states that the current through a resistor at constant temperature is directly proportional to the potential difference across the resistor, and we can see that directly proportional relationship very clearly here. As we move down to our filament bulb, our lamp, we have a characteristic sigmoidal graph shape. So we can clearly see that current and potential difference are not directly proportional. We have a curved line where at higher currents and higher potential differences, the resistance increases. And clearly this is not obeying Ohm's law. Part of the reason for this relationship is at higher currents we get a heating effect in the filament bulb, which increases the resistance of that bulb. And then lastly, the diode. If I draw the circuit symbol of a diode here, remember that allows current to flow in one direction only. In this case, it's flowing from left to right. You see this kind of relationship with current and potential difference or voltage. You have high resistance when the current flows in one direction, so in this case right to left, and low resistance when the current flows in the other direction, so in this case left to right. The student investigated how the current in a filament lamp varies with the potential difference across the lamp. Remember, potential difference and voltage mean the same thing. And as you would expect with a filament lamp, we see a relationship which is not directly proportional. We don't have a straight line. Instead, we have a sigmoidal curve, which is indicative of a non-ohmic relationship between potential difference and current. Remember, that's a slightly different part of the specification, but you do need to be aware of Ohm's law. Describe a method the student could use to obtain these results. You should include a circuit diagram. So have a look closely at what we have. We need a filament lamp, which, remember, this is the symbol of. We need a voltmeter in order to measure the potential difference. We need an ammeter to measure the current. The voltmeter needs adding in parallel. The ammeter needs adding in series. And then you need a way of altering the resistance of the circuit, so you're going to need a variable resistor. Really think critically about what you're going to need here. So that's your variable resistant component symbol. So I'm going to start with my circuit diagram. Here's my lamp. We need a power supply, so I'm just going to use a battery, which, remember, is multiple cells. There's my ammeter, which I've added in series. Here's my variable resistor. Doesn't matter what order you put those in. And then remember, they mention the potential difference of the lamp, and that needs a voltmeter, therefore adding in parallel around the lamp. So you do need to practice drawing your circuits. But look, my ammeter is going to measure the current. It's been added in series. The voltmeter will measure the voltage that's been added in parallel. And here's my power supply and my variable resistor. So really spell it out. I will measure the current using an ammeter. I will measure the voltage or potential difference using a voltmeter. In terms of the marks we've been awarded so far, we have 2 marks here. We get a mark for the fact the voltmeter has been added in parallel, a mark for adding the ammeter in series, a mark for the addition of the variable resistor. So we're already on 5 marks. I don't want to overcomplicate this. I'm just going to mention for my 6th mark that I'm going to repeat, calculate an average, and discard any anomalies I identify. So despite the fact that I've been given lots of space there, that's how I'm going to get my 6 marks, by drawing my circuit diagram nice and accurately. Determine the resistance of the filament lamp when the potential difference across it is 3 volts. Use the physics equation sheet and figure 6. So we're after R, that's my voltage reading. So let's use the graph to find out the current when the voltage is 3 volts. Read that really carefully. It's 0.16 amps. Here's the equation I'm using. Sub in your values, divide both sides by 0.16, so our resistance is 18.75 ohms. The current in the lamp is 0.21 amps when the potential difference across the lamp is 6 volts. Calculate the energy transferred when the filament lamp is switched on for 30 minutes. Look, I like to label what everything is. I've got a V, an I, an E and a T. So the equation I need is equal IVT. I'm after energy. My current is 0.21. My voltage is 6. Just be careful with time. We need that in our standard science unit of seconds, so we just need to multiply that number by 60. And so that is a very nice 5 marks right there, 2,268 joules. Figure 2 shows a rock found by a student on a beach. To help identify the type of rock, the student took measurements to determine its density. Describe a method the student could use to determine the density of the rock. So always bear in mind which equation we're using to calculate these values. So density equals mass over volume. So clearly we're going to need to take a mass reading, a volume reading, and substitute it into that equation. So find the mass of the rock using a balance. Now, in order to find the volume of the rock, obviously it's an irregular shaped object, so we can't just times its length by its width by its height. I'm going to place it in a Eureka can and measure the volume of displaced water. So we're going to measure the volume of displaced water using a measuring cylinder. Always mention appropriate apparatus. So clearly we are inferring that the volume of displaced water is the same as the volume of the rock. And then substitute values into the equation. Don't forget to state the equation. Density equals mass over volume. The student determined the density of the rock to be, what are the maximum and minimum values for the density of the rock? So the maximum density is clearly 2.55 plus 0.10. The minimum value will be 2.55 minus 0.10. Table 1 gives the density of 5 different types of rock. Which 2 types of rock in Table 1 could be the type of rock the student had? So we need to match up these values in here. This one has 2 higher density. At its maximum value, that could be 2.50. Which fits in our range. So it could be chalk, could be flint, it's not going to be sandstone, and it's not going to be slate.